All right, this is section 6.2, representations of functions. And in this first example, we have two shapes where we have to write an equation for them. It says write an equation that describes the function, and we're going to fill out the mapping diagram that is below. Now, in the last section, we talked about how the input is another name for the x variable, and the output is another name for the y variable. We're going to call it A for area in these shapes, and that the output is always dependent on what you're plugging in for the input. So that's why we call the output, or the y variable, the dependent variable. So in this first shape, we've got a triangle, and we're finding the area of this triangle. So the equation we can write is A equals 1/2 BH, or BH over 2. And then because we know the base is, it's 2 on this side and 2 on this side, that makes 4. So we can plug in 4 for the base. And it says the height is h, or as x there. So we're going to use x for the h variable. And then we can even simplify even farther, because we know that all triangles, you have to take half of them. So we can do half of 4 to get 2. So our final function for this specific triangle is A equals 2x. And then now we can plug in all of our inputs. If x is 1, we output a 2. 2 times 1. 2 times 2 is 4. 2 times 3 is 6. And 2 times 4 is 8. Now for the trapezoid, the area of a trapezoid is 1/2 base 1 plus base 2 times height. Remember, a trapezoid is very similar to a triangle. Both formulas have a 1/2 and an h. In a triangle, we only have one base because the other side, it comes to a point on the other side. And then for a trapezoid, we always have two bases. So if a triangle is 1/2 base times height, a trapezoid is 1/2 bases times height. And we have our bases here of being x and 2x. So x plus 2x. And we also have our height being 2. So if we simplify this, we can scratch out the half and the 2, because they will cancel each other out, leaving us with just x plus 2x, which is 3x. So the area formula for this specific trapezoid, our function, is A equals 3x. So if we plug in 1, we get 3. If we plug in 2, 3 times 2 is 6. 3 times 3 is 9. And 4 times 3 is 12. So a function rule is an equation that describes the relationship between inputs, which we said were the independent variable, because you can plug whatever you want in for those, and the outputs, which is the dependent variable, because whatever the output is going to depend on what you plug in for it. So a function rule is just an equation, okay? And so we were writing function rules in the last two problems. In fact, the last function rule we wrote for the trapezoid was y equals 3x. So no matter what we plug in for that, right, we input a -2, you plug it in for x right there, it outputs a -6. So that's how a function rule works. It's pretty basic. You just plug something in for x and it outputs the answer, which is the y. So let's write a function rule for each of these statements. Remember, the function rule is just an equation. It says the output is 5 less than the input. Well, remember, the output is another word for the y variable, and we know is means equals, and then it says 5 less than the input. The input would be the x, and 5 less than x would be x minus 5, not 5 minus x. It does matter what order you write it in because it's subtraction. If it says 5 less than the input, then we need to take 5 away from x. Example B says the output, y, is equals the square of the input. Well, if the input is x, then the square would be x squared. And then finally, the last one, the output is 8 less than twice the input. So y equals 8 less than twice the input. So twice the input, let's write that first, 2x, and then 8 less than that would be minus 8. And you can see this is written in slope-intercept form. So of the three that we've written, we've got one that is linear, okay, the second one that is not linear, And then the third one, that is also linear, right? And I can tell because we can write these in slope-intercept form. We have a slope of 1, a y-intercept of -5. We've got a slope of 2 and a y-intercept of -8. But because the second one has an exponent there, that's a dead giveaway that this is not linear. In this next example, we're going to continue writing function rules. This says write an equation that describes the function, and there's two parts here. There's a part A and a part B, and they give you two different series or patterns of different shapes here, different figures, and it says then use your equation to find out which figure has an area of 81 when the pattern would continue. So you can see by the pattern here, each of these squares has an area of 1, so we're just counting the squares. For the first pattern, we start with 1, and then 3, and then this is 5, and then this is 7. So it's going up by 2 each time. So if I write y equals 2x as my function, it won't be it won't be right. It is going up by 2, so that's technically my slope. That's the rate it keeps increasing by. But we're starting with 1, right? So it's not, if I plug in 1 for x right there, I'm going to get 2. Well, I need to get 1, and then I need to get 3, and then I need to get 5. So if I write -1, then if I do plug 1 in, I'll get 2x, or 2 minus 1, which is 1. And then I'll get, if I plug in 2 for figure 2, if I plug in 2 for x, I'll get 4 minus 1, which is 3. And if I plug in 3 for x, I get 6 minus 1, which is 5. So we actually can write the equation, or the function rule, y equals 2x minus 1, and that represents our entire pattern here. If this pattern were to continue on forever, you're always adding 2 squares to the bottom left and to the bottom right corners there, and it's always going to increase by 2, which is why our slope is 2, but it started at 1, so if you take away 1, we already had 1 to begin with. Now for the second one here, it goes from 1 to 4 to 9 to 16. And so it's not increasing by the same amount each time like the last one was, where it was increasing by 2 at each time. So the last one was definitely linear. You can see we can write this in slope-intercept form. This one's not linear, but it's still a function we can write. You hopefully have recognized these numbers. They've been on my clock all year. These numbers here, 1, 4, 9, and 16, are the first 4 perfect squares. 1 times 1 is 1, 2 times 2 is 4, 3 squared is 9, 4 squared is 16. So what they're doing each time to this number is that they are squaring it. So my function then would be y equals x squared. Okay, that's the function. And then the second part of this says, which of these figures would have an area of 81 when the pattern continues? Well, in the first one, right, in the top figure here, in part A, it will eventually get to 81, right? It will eventually get to 81 because it's covering all of the odd numbers, 1, 3, 5, 7, the next one would be 9, then 11. So if it wants to know what figure it'll finally get to 81, we can just plug in 81 for y, and then figure out, so that's what we want our output to be, right? So plug that in for y, and then we can figure out what our input would be. Remember, we're inputting the figure number, so we can figure out what figure that would be. Subtract 1 from, add 1 to both sides to get 82, to get rid of the -1, and then divide by 2, and we can find out that on figure number 41, we will finally reach 81 as an area, 81 of those orange squares. Now, in the next part, we are definitely going to get there a lot faster. Think about, what would I input for x in order to get 81? Well, so I can plug in 81 for my output. That's what I want to output. And I can try to figure out, what am I going to square to get 81? Remember, we just square root both sides, and you probably already knew it was 9. So on figure number 9, we will get an area of 81 versus up here, it takes 41 figures before we finally get an area of 81. All right, so let's evaluate the functions now if we have different values of x to plug in for them, just like we were doing a moment ago. So y equals 2x plus 5 if we input x equals 3. Remember, x is the input, y is the output. Then we can plug in 3 for x. We can times it by 2. We can add it with 5. And that means we're outputting an 11. So when we input 3, we output 11, right? That's an ordered pair. So 3, 11 is somewhere on that line. And then for b, this is not a line. This is non-linear, right? Because of the squared, the exponent there. We can still plug in -1, though. So if we plug in -1, y equals negative, so when I'm plugging in, I'm going to use parentheses here. So I'm squaring -1. -1 squared is +1. But then there was a negative in front of the x as well. Right? So I square -1 to get 1. There was a negative also in front. So my answer is going to go back to negative, and it's going to be -1. Right? So when I input -1, I also end up outputting -1. So that point is somewhere on this function, which is a curve because it's nonlinear. All right, so function rules can also be written as f of x, which is read f of x, just like it says there. So when you see f parentheses x, that's f of x. And that's just another way of representing the y variable. F standing for function, and then the x is telling you that that's the input, right? X always stands for the input. So when you put it in parentheses like that, that shows you that that's what the input is. So f of x. So what this is the function if I'm inputting x. So f of x is just another fancy way of saying the output, or the y variable. So f of x is the same as the y variable. When you get into higher level math, starting next year especially, you're going to see a lot of functions being represented as f of x instead of saying y. But it means the same exact thing. So for example, C, we're supposed to plug in x equals 5. So then the way I technically write that is f of 5. That tells you what I'm plugging into this function. So when I plug in 5, I get 7 minus 3 times 5, or 7 minus 15, or 8, or -8. So f of 5 is -8. Okay, so the ordered pair, 5, -8, is on that line. Even though this isn't written in slope-intercept form, I could easily change it so that it's in slope-intercept form, and it makes a line. This next one's definitely not a line with the exponents there, but you can see that's an interesting way of writing it. When they say f of -2, that they're telling you right there what they want you to plug in for x, right? So x is what goes in the parentheses, right there. You can see it goes in the parentheses. So that tells you what to plug in. So they're saying, what's the function when you plug in -2? So f of -2 means I plug in -2, and I'm going to cube it to the third power, and I'm going to plug in -2 again, and I'm going to square it. And that's what f of -2 means to do. So I don't actually have to write, hey, plug in x equals 5. You can just write it in the parentheses right there. So when I do that, -2 to the third power, let's start there because I know order of operations says exponents first. -2 times -2 is 4, and 4 times -2 is -8. And then I'm supposed to times that with -3, which is positive 24. Next up, I've got -2 squared. -2 times -2 is 4. So I got 24 plus 4, which is 28. So f of -2 equals 28. So the ordered pair, -2, 28, is somewhere on that really interesting curve that we have in this example D. And a function can also be represented by an input-output table and by a graph. So let's look at that now. Here we have an input-output table where the input obviously is x, the output is y, and the ordered pair they give you for each of these. And then they take those 3 points, 1, 3, 2, 4, 3, 5. They plot this them on this line over here. So you can see functions can be written as equations. Functions can be written in t-tables or charts like this one here. And functions can also be represented as graphs. So there's many different ways we can represent functions. Now, the equation, which is another way you can represent it, the equations for each of these, they represent the same thing. We've got a slope of rise 1, run 1, and we have a y-intercept of 2. So f of x, or y, equals 1x plus 2. So remember, this f of x just is a fancy way of saying y, right? That's just the y variable. But I want you guys to see that. You may not see it in your homework, but I want you to recognize that so you can remember that for next year. When you see f of x, that's just the y variable. All right, so let's graph some different functions. For this first one, we've got a linear function, f of x equals negative 2x plus 1. So we have a slope of negative 2 and a y-intercept of 1. So down 2 over 1 all the way through my graph will give me points right here and then the other direction. And let's see how straight I can try to make this. Okay, there's that, and then there's there. So we have a linear function that looks like that. And we can obviously use slope-intercept form to graph that one. This one's going to be a little bit tougher to graph for the second one because of the exponent. I know it's nonlinear. So it's best probably to make a t-table. Let's plug in negative 2, negative 1, 0, 1, and 2. Let's plug those 5 values in for x to see what this is going to look like when we plot it. Remember, this is the first way we actually used to plot lines, was to plug in an x and to output a y, right, before we knew what slope-intercept form was. So if I plug in negative 2, the first thing I'm supposed to do is square it. Negative 2 squared, negative 2 times negative 2 is 4, and then I'm supposed to make it negative. So negative 4 plus 1 is negative 3. So when I input negative 2, I'm outputting negative 3. So right there. When I input negative 1 squared is 1, make it negative. Negative 1 plus 1 is 0. So when I input negative 1, I get 0. When I input 0, 0 squared is 0. There's no such thing as negative 0. Plus 1 is 1. Okay, so we actually see they're going to intersect right there. And then when I input 1, 1 squared is 1, make it negative. Negative 1 plus 1, we're back to 0. And when I input 2, positive 2 for x, 2 squared is 4, make it negative. Negative 4 plus 1 is negative 3. So it's actually a parabola. Upside down parabola, because you actually see this negative there. That's what that negative does, and you'll learn that next year. And then finally, this interesting one, we haven't talked about what that shape's going to look like yet. I think I've mentioned that when you square your exponent, your x variable, you get a parabola. In this case, ours looks like this. But I've never talked about what happens when you cube one, or at least I don't think I've talked about one. So let's plug in those same 5 values. Negative 2 cubed, negative 2 times negative 2 times negative 2, you got 3 negatives there, is going to be negative 8. So when I plug in negative 2, I get negative 8, which is going to be right around there. When I plug in negative 1 for x, when I plug in negative 1 times negative 1 times negative 1 is negative 1. So when I plug in negative 1, I get negative 1, so that's right there on the graph. When I plug in 0, 0 cubed is just 0. When I plug in 1, 1 cubed is 1. That's interesting. And when I plug in 2, 2 to the third is 8. So what we're actually getting is we're getting another curve, but it's curving like that. So that's interesting. That's not a parabola, but that's what the function f of x equals x cubed looks like. So we know what x squared looks like as a parabola. X cubed kind of looks like, well, I don't know what that looks like. Kind of just a curve, that vertical curve there. All right, let's look at this story problem. It says the number of pounds of carbon dioxide produced by a car is 20 times the number of gallons, G, we're using G for gallons and P for pounds, of gasoline used by the car. Write and graph a function that describes the relationship between G and P. So it says that the pounds, P, so I'll start there, P, the pounds, is or equals 20 times the gallons you put in. So the number of pounds of carbon dioxide produced by a car is 20 times the number of gallons. So each gallon produce, or every 20 gallons, I should say, every 20 gallons would produce 1 pound of carbon dioxide. That's interesting because a lot of cars hold around that. I know my car holds around 15 gallons, so I'm producing about a pound, just a little under a pound of carbon dioxide every time I fill up. So that's not good, obviously. We want to graph this. We know that there's no y-intercept, so I can start right there at 0. So obviously, if I don't put any gallons in, I won't be producing any carbon dioxide. 0, 0 is a perfect spot for our function. That just makes sense. This is going to be a direct variation. And then I'm going to rise 20 and run 1 and rise another 20. So if 2 gallons produces 40 pounds and 3 gallons produces 60 pounds. And just like you'd expect, the number of pounds we produce depends on the gallons we put into it. So the number of pounds of, so remember we call the y variable the dependent variable, and it depends on the x here. All right, so I'll leave you with this summary and then this kind of funny little comic strip down here. In the summary, we said there's different ways you can represent functions. You can write it in words, so we did that. Right? You can write a function using an equation, or using f of x also as y works, so you can do that. You can use an input or output table, so you can use a chart, basically is what that is, a t-table I call it. You can use a mapping diagram, which we've looked at in the last section, or you can use a graph. And I just want to remind you that we have definitely used graphs, and we've definitely used functions, and we've definitely used charts, and we've kind of used words to represent equations. This is really the only new thing is the mapping diagram for us. The rest of this is kind of review. So hopefully you find this whole chapter really a lot of review. And then this funny little comic down here, you can see I graphed our profits, and it looks as if the profits are going up, but he has tilted this graph on its side, and if you tilt it back up the correct way, you can see the profits would be going down. So I guess it really just depends on how you look at things. So these are different ways you represent functions, and this is section 6.2.